Hello grade 10, this is Miss Hughes and welcome to the world of indices. So today we're going to look at just where the rules come from and why they work. You've got this nasty long list of rules. I promise you'll get used to using them. Today all we're going to do is figure out why they work and where they come from. Hopefully you can follow the logic throughout the whole thing so that you know that we haven't just made up these rules and that they all make sense. It's going to go pretty fast, so grab a pen, get ready to take some notes, and let's go. We start with the premise of, well, what is an exponent? What is a power? So just make sure you understand what it says here. So for example, in this line, a to the 5 is a multiplied by itself 5 times. It's just a shortcut. It's quicker to write this than it is to write this. The a is called the base, and the 5 in this case would be called a power, or you could call it an index, or you could call it an exponent. All of those words are okay and you need to be familiar with them. So we're going to play around with different versions, different combinations of the powers of a and see that these rules, see how we come up with these rules. For example, if we start with a to the 5 times a to the 3, well, a to the 5 is just a times a times a times a 5 times, and then we're going to multiply that by a to the 3, which is a times a times a, and that in shorthand is a to the 8. If we divide, let's say we have a to the 5, so that's a times a times a times a times a, and we divide by a to the 3, a times a times a. 3 of these a's cancel out, and you can see that the answer to that is a to the 2. Now, we can already spot a shortcut, because if we add the two powers together, 5 plus 3 is 8, and 5 minus 3 is 2. So if we were to generalize this, and instead of using 5 and 3, we used n and m, then we would get this rule, and with the second version, we would get this rule. Now let's try this, a to the 5 to the 3. Well, that's just a to the 5 multiplied by itself 3 times. And if we use this rule, we can add those 3 powers together and we get a to the 15. Again, you can see a shortcut, 5 times 3 is 15. So in general form, that's that rule. All right. Okay, I think that was a same thing again. All right, what if instead we have a to the 5 divided by a to the 5? Well, if we use this rule here, then that's the same as a to the power 0. But if we use the fact that a to the 5 divided by a to the 5 is just something divided by itself, then that's got to be 1. So those two things have to be equal to each other. So anything to the power 0 equals 1. Now if we use a to the 3 divided by a to the 4, let's do it as a division. A to the 3 divided by a to the 4. That gives us a times a times a divided by a times a times a times a. And 3 of those a's cancel out. But just be careful because you're not left with 0 at the top, you're actually left with 1, because a divided by a is actually 1. These are all 1s. We don't normally write them because it's not necessary, but there is a 1 there. 1 times 1 times 1 is 1 over a. So a to the 3 divided by a to the 4 is the same as 1 over a. But if we had used this rule here, we would have had to say that that's the same as a to the 3 minus 4, which is the same as a to the negative 1. So what that gives us is that this is the same as this. So whenever you have a to the power of negative 1, it's actually 1 divided by a. Now this is called, word of the day for now, is called the reciprocal of a. We can call it a flipped over if you like. So a over 1 becomes 1 over a. That's called the reciprocal. All right, similarly, if we use the same process for this, let's do it the division way first. So a to the 3 divided by a to the 5. That's a times a times a over a times a times a times a times a. 3 of those a's cancel out, all 1s. That gives us 1 times 1 times 1 is 1. A times a is a squared. Okay, but if instead we'd used the rule this rule here, the division rule, then I would have had to subtract those two powers. So that's 3 minus 5, which is a to the minus 2. So doing this question two different ways, I've used equal sign all the way through, so that means this is actually equal to this. All right, and now that I've shown an example, I can use that rule. So a to the negative, in this case negative 2, is the same as 1 over a to the 2, or the reciprocal of a to the 2. In general terms, a to the minus n equals 1 over a to the n. All right, what if we've got a multiplication? Well, ab cubed is ab times ab times ab. This is a long string of multiplication. It doesn't matter what order I multiply in, so that's the same as a times a times a times b times b times b, which is a cubed, b cubed. So you notice we were able to distribute the 3. Same with division, with fractions. That's a over b times a over b times a over b. Multiplying fractions, a times a times a is a cubed, b times b times b is b cubed. So again, I was able to distribute that. So that's that rule and that rule. This one's a little bit trickier, so let's approach it this way maybe. Let's call this a over b to the power of negative 1 to the power of 3. If you remember in this rule here, we said that we could multiply those two together. So minus 1 times 3 is the same as negative 3. So those two things are the same. Now, when I raise something to the power of negative 1, we said earlier we need to find the reciprocal. Now, the reciprocal of a over b is b over a. So I've rewritten this whole thing as b over a. And now we still have to raise it to the power of 3. I can distribute that 3, b to the 3 over a to the 3. So notice how two things have happened. That minus has flipped the fraction over, it's found its reciprocal, and the 3 has cubed it. So the fraction ends up upside down and cubed. And there's the general term for that one. All right, last 3. They are the trickiest one. Here we go. All right, so consider just for a moment the square root of 5. Hopefully you agree that if I square this, the square root and the square will undo each other. They are inverse operations, so I will get 5. And hopefully you also agree that 5 is the same as 5 to the 1. Now, let's consider, for example, just for a moment, something that looks like this. 5 to the power of a half. And let's see what happens when we square that. Well, if we use this rule here, it says a to the m, oops, sorry, that should be an n. A to the n to the m is a to the nm. So that says I can multiply those two things together. Now, a half times 2 is 1. So that gives the same as 5 to the 1. So can you see how square root of 5 is actually the same as 5 to the half? So whenever we want to write a square root as a power, as an index, we write it as a to the half. Okay, what if instead, let's just get rid of this, eraser. Okay, what if instead we were interested in finding, we were looking at cube roots. So again, hopefully you will agree that the opposite of the cube root is to cube something, and that those two are inverse operations, and I will end up with 5 to the 1. And again, let's say I had something which said 5 to the 1/3. If I multiply those two together, 1/3 times 3 is 1. So that is actually the same as this. And again, anything to the power 1 over n, we call it the nth root of a. You will do some examples of using this rule, but this is just so that you know where the rule comes from. And the very last one. So suppose we have a to the 2/3. Hopefully you'll agree that that's the same as a to the power of 2 times 1/3. 2 times a third is the same as 2/3. And I'm going to use this rule backwards. So I'm going to write that as a squared to the 1/3. Just convince yourself that that's the same as that. But a power of 1/3, we said here, is the same as just a cube root. So that's the cube root of a squared. Now, don't worry too much about the numbers, but just notice where things have landed. The 2 ended up as a power. The 3 ended up as a root. So the numerator gave us the power, and the 3 gave us the root. That's that. And soon you'll practice using these rules. Thank you very much. We're done.